Day 237 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem. This time we're at day 237 and we're still going strong, y'all. Today we have question number 222. Count complete tree nodes. The difficulty level is easy, so you already know we're going to keep the solution as simple and easy to understand as well. So let's get into it. Question says, given the root of a complete binary tree, return the number of nodes in the tree. According to Wikipedia, every level except possibly the last is completely filled in a complete binary tree, and all nodes in the last level are as far left as possible. It can have between 1 and 2 nodes inclusive at the level H. Design an algorithm that runs in less than big O of n time complexity. All right, y'all, so let's look at example 1 so we can actually see what it is that they want us to do. First thing we need to know before we even look at example 1 is we need to know what is a complete binary tree. So it gives us the two requirements that we have to satisfy right here, which are every level except possibly the last is a completely filled in a complete binary tree, and all nodes in the last level are as far left as possible. So let's come over here so I could break that down and give y'all some examples of what that looks like, right? So first thing I'm gonna do, I'm gonna create a complete binary tree for y'all, and then I'm gonna show y'all some examples of what a complete binary tree does not look like. So right now, I'm gonna show you what a complete binary tree does look like. So it would look something like this. We might have the 2 here, put the 3 here. Let me get that better for y'all. Put the 3 right here. Spread that out. Boom. Then we come down here. It might look something like this. We could go just like this. 4. Put the 4 there. Put the 5 there. Boom. Boom. Just like this. Space this out for y'all. Okay, so this would be an example of a complete binary tree. Why? Because it satisfies the two requirements that we're looking for. One, every level except possibly the last is completely filled, right? That's the first requirement. So if you look at this binary tree, we're only supposed to have the maximum we can have nodes, and the first root node is 1. So we have that one root node, so that level is filled. Second level, the maximum nodes we can have in a binary tree is 2, right? So these nodes are filled. We have 2 nodes right here, 2 and 3. Boom. Then we come down here, it says except possibly the last. So the last doesn't have to be filled. So that's why it has the 4 and 5, but there are not more more nodes over here, child nodes with the 3, because it says all nodes in the last level are as far left as possible. So since the nodes 4 and 5 are still as far left as possible, and the last level does not need to be filled, right? It says except possibly the last level. So the last level does not need to be completely filled. This satisfies both requirements, right? So we could count that as a complete binary tree. Now let's look at some examples that wouldn't satisfy those conditions, right? So we can make it make sense for everybody. So say, let me copy and paste that right there. Boom, boom, just like this. My bad, y'all. So now let's say we had something that looked more similar to, let me see how I want to do this, something more similar to this, right? So say we got rid of this 5 right here. Boom. Then we came over here and say we put the 6 and 7. Say we put 6 and 7 over here like this, right? This would not be a complete binary tree. Why? Because it doesn't satisfy the requirement of all nodes in the last level are as far left as possible, right? So this level's completely filled. This level's completely filled. The last level is not completely filled, but it doesn't have to be. However, these 2 nodes need to be pushed over as far left as possible. So if it looks something more like this, right? Say we had nodes like this and we put the 6 right here, and then we put the 7 over here. right? Hold on. If it looked like this, then it would be a complete binary tree. But that's not what it looked like. We had it looking like this, right? So let's get it back. We had it looking like this, which is not a complete binary tree because as you can see, the nodes are not pushed as far left as possible. This it's missing a node right here, right? So there's a gap in the nodes, meaning these nodes are not pushed as far left as possible, which would mean it's not a complete binary tree because it doesn't satisfy the necessary requirements, right? So now let's look at one more example of what would not be a complete binary tree, and then we can move on and we can start to understand our solution and the question a little bit better. So this right here would be another example. So say it looks something like this, right? And we just got rid of this right here, and we got rid of this this right here. So say it looks something like this, y'all. This is not a complete binary tree either. Why? Because it doesn't satisfy either one of the requirements, right? So in this first level, that's completely filled. But the second level is not completely filled because it's a null right here. If it was filled, there would be no null. Since there's a null right here, it's not completely filled, so it doesn't satisfy that requirement of every level except for the possibly last being completely filled, and it doesn't satisfy the the second requirement where all nodes in the last level are as far left as possible, right? So these nodes would have to be on the left subtree, but there is no left subtree because the level before it is not completely filled, which means this is not a complete binary tree either. So right now, this is the only example of a complete binary tree similar to this right here. This is except if we add a 6, because remember this 6 is still as far left as possible, so this 6 counts as a complete binary tree as well. These two do not, so we get rid of these, get one more look at these, and now let's get into the solution, y'all. Or actually not yet, because we didn't even look at the example yet. So let's look at the example. In example 1, we have the input root equals the binary tree 1, 2, 3, 4, 5, 6, and the output is 6. And y'all might think all we have to do is count the complete tree nodes, right? It's just 1, 2, 3, 4, 5, 6. The trick is we have to do it in big O of n time complexity, which is why we are going to use a post traversal to do it, because first we're just going to traverse this subtree, the left subtree, then we'll traverse the root, then we'll traverse the right subtree, and we'll be able to do that in big O of n time complexity. So let's look at the other two examples in case they try to throw out some tricks our way. So in example 2, root equals a blank array. The output would be 0 because it's a blank binary tree, so there are no nodes. There are 0 nodes to count, so we can put 0. And same thing with the input root. If there's only one root node, then we still have to count that root node, and the output would be 1. So now that we understand the question, let's get into the fun part, the solution. But before we get into the solution, y'all, if you need any new Apple AirPods, if you need any new Apple AirPods, go ahead and check that link out in the description. Then after you do that, go ahead and like, comment, and subscribe. Now, y'all, let's get into the fun part, the actual code. Code is not that difficult. It's only 2 lines, so we'll get through it pretty quick. So let's get to it, right? First thing we need to do is we need to handle a case where there are 0 nodes, like in this example 2, right? So in order to do that, all we have to do, we can use a guard statement and say guard let root equal root, else we're just going to return 0. So if there is no root, then we are just going to return 0. It's simple, that's simple. Now, the other part is simple too. We're going to use a little bit of recursion. This is where we're going to use the post traversal method in order to count the left subtree. Then we're going to count the root, and then we're going to count the right subtree. So in order to do that, all we're going to do is we're going to say count nodes. First we need to say return count nodes. Open up the parentheses. We're going to say root.left. Boom. So that's going to traverse the left side. Then we're going to say plus count nodes. open up the parentheses, root.right. That's going to traverse the right side and count it. Then we're going to say +1 just so we can add the root and add the root to the count, right? That's why this +1 is there, to represent the root. So now let's run this, see how it runs, make sure it runs like it's supposed to before we submit it, and it's accepted, right? So let's submit it, make sure it stays accepted after we submit it, because you all know how LeetCode can get. And look at that, y'all. 4 milliseconds beats 27.22% of users with Swift, y'all. Not too bad, not too bad at all. Don't worry about those numbers. We're just looking for a solution that will get us through this problem, that we will be able to learn and understand what's actually happening so we can apply that knowledge later down our LeetCode journey. And I feel like this is a perfect solution for that. Simple and easy to understand. It's only 2 lines of code. All we're doing is traversing the left side and getting that count. Then we're traversing the right side, getting that count, and we're adding 1 just to represent the root. And that's all we have to do, y'all. So I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.